looking at the chapter A, I'm going to review, go over that, and we'll take a look at scales as well as part of it. And so, when we're talking about technical drawing, it's been around, as they say, since the beginning of man, really. Technical drawings as we know it since the Industrial Revolution, but making drawings to build things, earliest recorded is mentioned in the Bible for King Solomon, his temple. They talk about it in there, and there's been other evidence found where plans for various structures are etched or carved into stone, tablet-like, and then brought to the site to look off of. And then, of course, we're pretty sure that the Egyptians had some form of drawing that they used to do their work over the centuries. But for us in the modern age, the Industrial Revolution, back in the 1700s, helped us advance or move forward how we're representing objects, as we moved away from being what we call an artisan type of makers, where you had little shops and they all had their own specialty and they made their little product or whatever it might have been, and a lot of it was done by model. They would make things, a prototype if you will, and then just make copies of that as needed. And with the advent of a projection system that came forward from descriptive geometry by a scientist by the name of Gaspard Monge in France, he came up with a way to do this projection to represent three-dimensional objects in two dimensions. And from that point forward, it moved along to where we have our sophisticated projection system that we have now. So all of our pens and paper and pencils and everything's been replaced by our CAD system. But initial design work or thinking or sharing of information in meetings, whether they're large or small, and in design teams and so forth, they still use a paper and pencil method to get their initial designs down or to collect information in the field. It's still a whole lot easier to collect this information with a sketch pad if you've got to measure up a building or check a building or take a measurement at a machine, to jot this information down or sketch it first and bring it to your CAD system, than trying to manipulate and manage a laptop or even a tablet out at the work site. That happens more and more with the tablet, where technicians may check valves or check layouts by looking off of a tablet drawing, but making changes to the drawing or making notes on it is still a little cumbersome to do. You can't get the fine point that you really want. You can on some small phones and some very small tablets, but if you're looking at a large architectural layout on a 6:9 screen, the detail, you're constantly zooming in and out trying to see. So learning to interpret drawings and to work with the projection system as far as a learning path, we still learn it from the manual drawing or basic drawing methods, at least to a foundational level. So when you interpret a drawing, engineers and architects have to be able to look at a set of plans and visualize the objects. So being able to read the objects, as you're seeing here, we might have a concept in a meeting, then the drafter prepares the production drawings, then the worker looks at these drawings, whether they're on paper or screen, and will visualize them. We may provide three-dimensional look, but by and large, a lot of the drawings that are out there for construction people or for manufacturing people are still two-dimensional. Well, just to mention about this, you can see, looking at our introduction, how it fits, that we work with drawings and we learn about detail and production and assembly drawings. Then you're going to look at sketching, how to think with a pencil. Then we're going to create mechanical drawings, and we'll use just basic sketching tools of grid paper and pencil, paper, and taking measurements. Some straight edges, some basic tools may be used, but by and large you won't need a whole lot. And then those can go to a computer drawing, which we won't pursue in this class, but you do in the Introduction to CAD class. And these drawings can then, of course, be shared over the web, and that is done day in and day out, and even collaboration, working on the same drawing at the same time with another engineering office. And of course, plotting it out, making a paper hard copy, and then prototyping or machining is possible from the computer drawing. So a production detail drawing, then, you see here, the detail means it's a single part. It's got dimensions, notes, title block, tolerancing, possibly an isometric view, a revision history, that is when we change a dimension or a finish or any part of it, then we kind of keep a history in our revision block. And the layouts, details that we create take on all kinds of representations out there in industry. Every company has their own little title block with standard information in it. And all of this is covered by video in the blackboard. So then your assembly drawing takes the details, and a lot of times we'll create an initial assembly drawing in paper, how the thing looks assembled, and then start creating details. But we may be measuring up something that's been completely disassembled, and we're reverse engineering it, or in other words, creating a different product that's very similar, and so we'll make sketches of it and then create the assembly drawing. The assembly drawing has the pieces and parts listed, part numbers, and sometimes more detailed information about each part as part of the assembly drawing, and may even detail what drawing number you could find the part on, or if it's going to be a purchased part or not. some assembly drawings are working assembly drawings, and if it's a simple kind of product, they might do that and actually have some of the detailed dimensions on the assembly drawing. In sketching, you don't have to have an artistic ability to do technical sketching. It's going to help, but you can pick up the skills that you need through practice, and you're not doing, real life type of sketching like you might see an artist do. We put notes and dimensions on our sketches, and we use what we call block letters. Their name is the single stroke uppercase Gothic is the name of the type of letters, block letters that we use, and it's all capitals. So as you begin to work through your drawings, you'll try to do more and more all capital letter type of printing on your title block and any other little notes that you're supposed to put on there. Your mechanical drawing tools, as we talked about really for this class, an eraser and a technical pencil, 0.5 and 0.7, and some lead, and possibly a straight edge, which I can provide for you if you think you want to use one. In certain places I'll tell you that you can't. So at the beginning we won't use any straight edges. Okay? We'll have to do it all freehand using the grid. So we don't have to use any of these other tools. I have them all available, but none of these are used. The racing shield might be the only thing on this page that really is useful. Then creating it on paper, a lot of times doing the technical sketch work, it really doesn't matter what size paper you choose. It's really going to be determined by the scale, the size of the part, and what scale you're doing it on for your design sketches and for the sketch work that you're doing. You're planning. But when we go to CAD and we print out the production drawings or construction drawings, then your company that you work for will have a standard size that they use. They may use the same size for every drawing they have, no matter what size the product is. And you may only have one little view on a fairly large sheet of paper. So these are the sizes. They go in 8.5 by 11 or 9 by 12 format, and the narrow side gets doubled, and the long side is carried forward to the next size. So that's how you can compare it and always know what size A, B, C, D, E is. And we don't use metric size paper in the United States. It's available, but it's not readily available. Alright, in measurements and scales, I've put on your desk four different scales, and there's the architect scale that doubles as a inch ruler, and we call them all scales. There are no rulers really in the drafting profession. They're all scales. I always tell everybody that rulers live in England, and the king and the queen, but we have scales in drafting. The scales are considered imaginary. In other words, we're imagining a unit of real-world measurement to be smaller than it is. So you're welcome to use these. The ones I've provided, you can borrow those. There won't be a lot of need for it at the beginning. Everything will be scaled for you. You may find a use for it on a couple of them where you have to enlarge them, but usually we just count the squares on our grid and do an enlargement. Later on in your career, you'll be using these scales to measure plotted or printed drawings that where the dimension is questionable or missing. So you have to measure the drawing and verify it. You don't ever measure a drawing and use that measurement straight up. You know, you have to verify that it is the correct measurement. So basically, millimeters, the metric scale, works on the base of 10, and then our fractional scale is based on the 12 inches per foot, and then we take and divide evenly the inch into fractional measurements and make it a fraction of a 1. So 1 over 2 would be half, 1 over 4 would be a quarter. And then down from there, 1 over 8 is an eighth. And then we divide that eighth in half and it becomes a 16th. And then the 16th becomes a 32nd. So 32 32nds here. We always write the least common denominator. So we won't put, for an eighth of an inch, we won't put 4 32nds. We'll put 1/8. Okay? The decimal inch scale is the most accurate inch scale that we have available to us. It's in the mechanical drafter scale, and they come in different different arrangements to identify measurements, to identify the hundredths of an inch. So it's 0.02 or 2/100ths of an inch is what each little mark is. So this one in particular has got it marked off so that we can read in basically tenths of an inch pretty easily. And then they've made the two middle graduations long. It's kind of different than the fractional scale. But that way it makes it easy to count. You know that each mark is 0.02. So 02, 04, 06, 08, and then 0.1. So this is a tenth of an inch. And it goes by 2/100ths of an inch. So provides a very accurate way to make a measurement to do a layout. Then feet and inches on our architect scale is an open divided scale, and on it we have our feet measurements out to the right and our inch measurements to the left in this particular scale. Okay, in some it's actually opposite, where the divided portion, the inches, are to the right. On each one of these you have to until you have them memorized, you have to figure out how many fractions you have, what is your smallest fraction that the inch is divided into. So each measurement, each half inch in this case, is a foot. So 1, 2, 3, 4, and it's a shared scale with the inch, so that's why you have all these conflicting looking numbers. But there's your 1, 2, 3 feet on a 1 inch equals a foot. So on the half-inch scale, when you look at it, if this is an inch, half inch equals an inch, then this measurement right here is actually a half inch. This is a quarter. I'm sorry, this is actually 6 inches. Thinking of half scale. This is 6 inches, this is 3, and then each one of these would be an inch, the next longer one. So therefore, it's pretty easy to remember, the half inch equals a foot scale has half inch graduations in it. The 1 inch equals a foot scale, okay, so here's a foot, actually tells us 3, 6, 9 inches. So each one of these next longest divisions is an inch. So the next smaller division is a half inch. So this is actually in the quarter inch measurements. So every little mark is a quarter inch. Then we'll just take one more look at the smallest division. Gives us the greatest amount of reduction. So 1/32 of an inch is, or 3/32 is equal to a whole foot. So again, it's an imaginary scale. We're imagining it. This is a whole foot. So right in the middle, that longest line in the middle is 6 inches. So each mark is 2 inches. 2, 4, 6. So each little division is a whole 2 inches. So you can see it provides the greatest reduction, so we can get like a building the size of this technical center on a sheet of paper in one view, okay, but it is not very accurate. So any measurements you make with this or layouts you make with this have to be verified. And you can make measurements on sheets of paper using this scale, but you have to take it with a grain of salt. You have to say, well, it could be plus or minus 2 inches, maybe even more, because the paper will grow in size based on humidity levels from the time it was printed. You know, and if it was printed when it was really dry, humidity was low, and now you've taken the paper outside to a construction trailer, it can grow a large sheet over the whole 4-foot length. It could grow a 1/16 of an inch and get larger. So that changes all the actual physical lines on the sheet of paper. Any questions about the scales? A little introduction to computer drawing and modeling. They've got a really advanced computer pictured there. The information, you know, when this was printed, when this was created, this book was created, must have been around 1985. So, you know, that was probably one of the most advanced computer systems available at the time. All right. The takeaway from it is that industry has fully adopted computer drawing and modeling, and that we are now all connected not only in a network in our office, but we're connected by the internet. And we can do dimensional modeling now, and we'll do that more and more. We do that first and then create our technical drawings from that. Then from the computer drawings, we'll use a printer. Not plotters aren't used anymore, although in CAD they're still called plotting, even though it's actually printing. So inkjets is what we print them out with. Then those drawings can be used by the technicians. They did update the book and talked about rapid prototyping, one little sentence basically. And we have the 3D prototyping here in the lab, and in subsequent courses that you study with me, like parametric modeling, we end up doing 3D printing of our models. Learn how that process works. Okay? And you can watch the blackboard, and you've already done all these sheets, so you're good on that, and you can watch the blackboard on how to do the sheets. The only comment I made, and I commented on it this morning, was that you would print inside the dashed lines and use all capitals. Uppercase, which uppercase, lowercase is carried forward from really when printing industry was invented, the technology for it, and they had little pieces of lead that had the reverse image of letters on it, little tiny slivers of lead, and they put them in a block to make a sentence or paragraph or a page, and it'd be a block of all this lead type, they called it. Well, the typesetter sat at a desk, and he had a big case in front of him, little bins with all the letters, and up here in the upper cases were the capitals. Down at the bottom, the lower case, were the small letters, or small capitals, some people call them, but the small letters. And that name stuck as it came forward through the decades, centuries actually, and been I guess a couple of centuries now of printing, since the letterpress was like the 1800s, early 1800s.